7.4, we're going to start out by identifying and learning what a power series is, and then we're going to tie that idea of what a power series is back to what we learned previously about a geometric series. So let's start with what is a power series. A power series is an infinite series whose pieces are expressions in terms of a variable with an increasing power. So this is going to look a whole lot like a polynomial, and you can look down right here. This is going to look a whole lot like a polynomial, with the exception is a polynomial has to have a degree, and this is infinite, so it doesn't have a degree. So we can't actually say that it's a polynomial, but it looks a whole lot like what we're comfortable calling a polynomial. So some things to notice, all of the series that we have talked about before, each term is a numerical value. In this sense, our terms aren't numerical value. N is what is changing. However, we're still going to have these x's, so my n values are changing. But each term in my series is still a piece of a polynomial, so to speak, a term with a variable in it. And that is what makes this a power series. So why is a power series useful? Why is it called a power series? It is very, very powerful. Why is a power series useful? So if we could represent a function that is more difficult to understand the behavior of as a power series, then we can more easily manipulate and understand its behavior. So the idea here, take something that doesn't at all look like a polynomial, turn it into something that looks a lot like a polynomial, a power series, in order for us to understand how that function behaves. So let's look at this power series up here that we are given in this box, and let's use what we know to identify the sum of this series and to describe what values of x will cause this series to converge. Well, if you look at this series, the sum from n equals 0 to infinity of x to the power of n, that's a geometric series, right? And if it's a geometric series, that means we can identify the common ratio and we can identify a. So in this case, a would be equal to what I get when I plug in 0, which is 1. And the common ratio in this case would be equal to x. So this is the first time we're seeing that our common ratio could actually be a variable when it's represented in a power series. So we could say that this is actually geometric with a equals 1 and r equals x. And what do we know about geometric series? If it's geometric, we know that the series will converge if the absolute value of the ratio is less than 1. So we know that this will converge if the absolute value of the ratio is less than 1. Well, in this case, that means we need the absolute value of x to be less than 1, which means we need x to fall between the values of -1 and 1. And if the value of x meets this criteria, if that is true, then we actually can find the sum, and the sum would be 1 over 1 minus x. So thinking about this as a geometric series, or geometric power series, we're going to call this, we can say that this geometric power series is going to converge if the absolute value of our ratio, which for this particular power series is x, if that absolute value is less than 1. And if that value is less than 1, it actually is going to converge to have a sum that we can find, 1 over 1 minus x. So I want you to think about what we just said. We just said if x falls between these two values, meaning for this interval of convergence from -1 to 1, so if our value falls within that range, then these two things are actually equal. 1 over 1 minus x is actually going to be equal to the sum from n equals 0 to infinity of x to the power of n for x values that fall within this range. Now, I don't know about you, but these two things definitely don't look the same to me. So your gut should be saying, Judson, prove this to me. I don't know if I believe you about this. So let's go ahead and look at this graphically and take a minute to convince ourselves that this is, in fact, true. All right, so let's look at this series, this geometric power series that we just talked about. Let's look at this graphically. And so instead of typing infinity in this numerator, I want to analyze what's happening as that a value is getting bigger. So If I'm at 0, it starts out, whoops, as a line. If I slowly move up, as I move up towards, and I'm actually not even going to go close to infinity, I'm going to stop at 100, but as I move up, what I want you to do is look at what's happening on the left-hand side of the function. The sum, even though the end is sort of flipping up and down between when it's an odd number and when it's an even number, what I want you to notice is that the value at the end, before that up and down flip-flop, is really kind of remaining constant. It's oscillating around some particular value up and down as this a value increases. So let's actually zoom in. I'm going to zoom in for you, and instead of me trying to drag unsuccessfully, I'm going to just hit the play and have you watch what's happening. I think it's easier to see all the way through. So going back to what we actually had said up here, we said that since this is a geometric power series, this is actually equivalent to this other function, 1 over 1 minus x, on the interval -1 is less than x is less than 1. We said, and that interval has a special name, and that interval is called the interval of convergence, or the IOC. You're going to commonly see that abbreviated. We said that these two functions, or this function and this series, are actually the same between those two values. So let's use that idea and analyze this graph a little bit more and see if we can convince ourselves that that is in fact true. So let's go ahead and add that graph in there. So, and then let's play with our a values again. So starting really small. As this value is going up, I want you to see what's happening. Again, we're paying attention to that left-hand side of the function. Or sorry, the left-hand side of both the function and the series. And it does look like as this number is getting closer and closer to infinity, or in this case 100 is where I'm stopping it, these functions do appear to be the same over that particular interval. And what is that interval? Let's take a closer look. That interval is -1 to +1, at which those two right here, I can't even tell what's green and what's red. They look to be the same over that particular interval. So I don't know if you stopped to really realize what we're saying here. We're saying that over this particular interval of convergence, from -1 to 1, this polynomial series is actually equal to this function in between -1 and 1, for x values between -1 and 1. And that's super freaking cool. I think that's so amazing and interesting that I could represent something like the function 1 over 1 minus x. I could represent it as a polynomial series, a geometric power series, in order to maybe manage or look at it in a different way. And this is our first leap into that idea of, can we represent more complicated functions using a power series? And this idea is going to extend in so many other sections as well as we move on, but I just think it's really cool to stop and see, I can't tell the difference on this interval of convergence between the sum or that function. And that's just something that's incredibly interesting and unique. Okay, so let's get back to the point. I just wanted to show you that graph to really help solidify this idea that we can use a power series to represent a function, and that function is going to be equal to that power series over some particular interval, meaning that they're becoming the same over some particular interval, and that interval is called the interval of convergence. So the power series that we just looked at, the geometric power series, was centered at 0. And you can think about this if you think back to when you first started talking about transformations in Algebra 1 or Algebra 2. And you talked about horizontal translations, and that's sort of what I mean by this is centered by 0, because there's no horizontal shift happening there. As opposed to if you come down here, you're going to see this one does include a horizontal shift. So we can generically define a power series in this way. A geometric power series, specifically, we're going to focus on geometric right now, a geometric power series centered at some value c, as opposed to just being centered at 0, centered at some value c, is going to be a times the ratio x minus c to the power of n, which we could represent expanded out right here, the expanded version, as opposed to just the summation version. Is this series still geometric? It sure is. I still have some ratio being put to the power of n. If so, identify the first term. Well, the first term would be a, and the common ratio would be x minus c, would be our common ratio. And anytime we can categorize something as geometric, we have a whole lot of information that we know about it. If it is geometric, we can determine whether or not it converges. And we know when will it converge. It will converge when the absolute value of this ratio is less than 1. And if it does converge, then we can also find the sum. So let's work through, this is just some really basic algebra here. I'm going to come down to where I have a little bit more space. So back in Algebra 1, you should have learned that to remove that absolute value, you're going to trap this between positive and negative 1. To solve this, you can add c to both sides. So negative 1 plus c is less than x is less than 1 plus c. So we can now state that our interval of convergence is going to be negative 1 plus c is less than x is less than 1 plus c, which we just have written much nicer down here. This also means that we can find the sum of the series. The sum is going to be that first term, a, over 1 minus the ratio, and in this case, we just said that our ratio for these geometric power series is going to be x minus c. So let's look at how we can actually apply this information to some examples. And I will point out there is another way that you can approach a power series like this. In my opinion, it's a less useful and more complicated way. And right now, I really just want to make sure that you are understanding what I'm talking about. So if you want to look over that other option, you can look at the PDF copy of my worked out notes, or you can stop by student support and we can talk about it then. But let's go ahead and look at these two examples down here and figure out what we can do with these functions and how we can represent them as power series. Okay, find a power series for the following function. Use sigma notation and show the first 4 terms and the general term of the series. Then find the interval of convergence for x. So the key thing that I want you to keep in mind when you're working on these problems is that your goal is to really think of this as our function is equal to 1a over 1 minus r. So in this case, looking at this function, I could rewrite this. I could rewrite this as 1 over 1 minus, well, if I wanted the denominator to be 1 minus something, since I need a positive 2, I'm going to put a negative 1 in here, right? 1 minus negative 1 gives me 2, and I also need a positive x, so that gives me x. And you can double check this for yourself. If you distribute, you're going to get 1 plus x, which is exactly what we were trying to get to begin with. So I can rewrite this function as 1 over 1 minus the quantity 1 minus x. And maybe you're thinking, why would that help us? We just took something pretty like 1 over 2 plus x and we turned it into 1 over 1 minus the quantity negative 1 minus x. It looks like we made it more complicated. But did we really make it more complicated? Now it's really easy to identify the two things that we need for a power series. You can identify what a is and you can identify what r is. What is a? A is 1. What is r? R is negative 1 minus x. Which means we can rewrite this as a sum or as a power series. So we can rewrite this. We can rewrite this geometrically as the sum from n equals 0 to infinity of my a, which is 1, which I don't really need to write, but I am going to anyways, times the quantity negative 1 minus x to the power of n. And if I expand this series out, that's going to give me, well, if I plug in 0, my first term is just going to be 1 plus, since I'm taking the sum, if I plug in positive 1, I'm going to get negative 1 minus x plus negative 1 minus x squared plus negative 1 minus x quantity to the third. How many terms is that? 1, 2, 3, 4 plus plus the general term here, we already identified up here, but is going to be negative 1 minus x to the power of n plus . So notationally, I really want you to see it's incredibly important, as I mentioned in a previous section, it's incredibly important for you to have this plus ellipses from the term you're leaving off on, taking you up to the general term, and then again at the end showing you that this pattern doesn't stop at the general term, it keeps continuing on forever. Both of those are important parts of how you need to write and format your answer. Now, if we want to find the interval of convergence here, the IOC, and to find that interval of convergence, to find that IOC, we know that our ratio needs to be trapped between -1 and +1. So -1 is less than, my common ratio in this case is -1 minus x is less than 1. I can add 1. I can divide by -1. That's going to flip my inequality signs. And then I'm just going to rewrite that like this. So here I have my sigma notation, my summation notation. I have my first 4 terms and my general term, and I have my interval of convergence. Why don't you go ahead and pause the video and see if you can work through B on your own. So first things first, on B, this is already perfectly written in our A over 1 minus R format. So I don't have to manipulate it like I had to do on A. So A is 1, R is 5x, not -5x. A is 1, R is 5x. So if I'm going to write this using sigma notation, the sum from n equals 0 to infinity of, what's our pattern here? 1 times 5x to the power of n. Now, you're more than welcome to start this at n equals 1. You just need to make sure that you adjust this accordingly if you're going to start at a different value. You need to have the same first term that you're saying you're going to have up here. Apparently, my pen was not working. So what I mean is if you want this to be n equals 1 instead of n equals 0, you need to accordingly adjust your exponent up here so that you do, in fact, have a first term that is 1 when you plug in n equals 1. All right, and let's go ahead and write out these terms. Actually, let's zoom in a little bit. It's going to give me -1 plus 5x quantity squared plus the quantity 5x to the third plus the general term, so plus ... 5x to the power of n, or I should say the quantity of 5x to the power of n, plus ... So you need to make sure you have that plus and ellipses before your general term and after it. And if you aren't being asked for the general form or the general term, you don't have to list it. So it's really important, don't do too much when it's not being asked of you, because if you write that incorrectly, you will lose points for that. So just be cautious and pay attention to the directions. And lastly, on part B, let's calculate that interval of convergence. So we're going to take our ratio, which is 5x, and we're going to trap that between -1 and 1, which means our interval of convergence is going to be -1/5 is less than x is less than 1/5. So what you're going to see in the rest of this section of notes is just 8 more examples of you working through identifying everything that we just did on these last 2 problems and really making sure you understand how to rewrite a function as a power series using sigma notation, identifying that general term as well, and then also making sure that you find that interval of convergence. So why don't you go ahead, pause the video, start working on those problems, then we can go over them together. Okay, so I'm going to work through the first couple, and then I'm going to just put up the solutions for the rest and talk through some key points. So number 1, and I'm not going to list this off so much as A, B, and C. I'm just going to do each of the pieces that's being asked. So find a power series. What I really mean there is state your A and your R value. So A, in this case, is 1, and R is 2x, which means that if we're writing the first 4 terms and the general term, I'm going to actually just use sigma notation. I'm going to do both at the same time. From n equals 0 to 1 of 2x to the power of n, and that's going to be 1 plus 2x plus the quantity 2x squared plus the quantity 2x to the third plus my general term, which is 2x quantity to the power of n plus dot, dot, dot. So I just did all three things there, sigma notation, the first four terms, and the general term. And then lastly, finding that interval of convergence. -1 is less than 2x is less than 1, so -1/2 is less than x is less than 1/2 will be your interval of convergence. So notice there's only a slight difference on number 2, and that slight difference is that r is now -2x. Since this is supposed to be 1 minus r, that means r is -2x. So if I write this using sigma notation, the sum from n equals 0 to infinity of -2x to the power of n, which is going to be 1 minus 2x, plus -2x squared, plus -2x to the third, plus dot, 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 plus my general term, -2x to the n, plus dot, dot, dot. And then lastly, to find this interval of convergence, we're going to take -1 is less than -2x is less than 1, and that's going to give us -1/2 is less than x is less than 1/2 as our interval of convergence. So go ahead and pause the video, work through 3 through 8. I will work through them as well, and then hopefully answer any questions you may have along the way. So 3 and 4 are really similar in setup. You need to manipulate that to be of the form 1 over 1 minus r. So on 3, that's going to be 1 over 1 minus the quantity of 1 minus 2x. On 4, that's going to be 1 over 1 minus the quantity 1 plus 2x. Then you can identify your common ratio and you can list off those terms. Don't forget your ellipses, don't forget your general term, and then you can find that interval of convergence. And you really don't need to show a lot of work for me when you're finding that interval of convergence. I know that you know how to do algebra 1, which is really the level of math that's being done there. On number 5, the only difference really is that you need that 2 to actually be a 1, so you can change that to be 1 over 1 minus the quantity -1 plus x. To identify that a is 1 and r is -1 plus x. You can list out that series, and then you can go ahead and find the interval of convergence. So go ahead and pause the video, finish those last 3, and then unpause the video and see how you did. So here you can see the worked out solutions for 6 through 8. One thing I just really want to point out is number 8 specifically, because number 8 is the only one on this whole page that has a first term that is not 1. So you'll notice that first term shows up in every single term because you're multiplying that by each specific term. So 3, and then 3 times 2x, and 3 times 2x squared, and 3 times 2x to the third. So I just want you to see, I wanted to make sure that I pointed that out. The rest of them I think are really similar to the ones that you have been working on already. So key ideas from this section. A power series is something that allows you to replace a function, so to speak, using a polynomial series, I'm putting polynomial in air quotes here, in order to analyze the behavior in a more logical or easier way. So power series is the big idea in this section. Now those functions are only equal over some interval of conversion, and that has to do with, in this case, that geometric interval of convergence, which has to do with the absolute value of r being less than 1. So make sure you jot down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.